Look up at the sky, Rosie. The sky is sure full of stars tonight.
On clear nights, the sky can captivate our imagination, dreams of other worlds. If only we could zoom in on those stars and see a clearer view, what vistas might await us, treasures to delight our insatiably curious appetites. Could we one day take high-resolution photos of the planets orbiting distant stars, perhaps even observe life forms on the surface? And could aliens be photographing us right now, watching us go about our day and quietly monitoring our behavior? A basic challenge with imaging is just the vast chasm of space that exists between stars, for even our closest stars are so far away that they appear as mere specks of light. Now, in the era of modern astronomy, we have devised clever tricks to infer planets around those specks, such as looking for the wobbling motion of them caused by their planet's gravity. In a few dozen cases, we actually have pictures though, not just specks of light from the star, but other specks emanating from the planets, photons from distant other worlds. This is the state of the art. A photo of the young star system PDS-70 taken by Miriam Benestry and colleagues with the ALMA Observatory this year. That blob of light is one of two known planets in the system, and this one shows evidence for a disk of material, perhaps in the process of forming moons. Despite the technical achievement here, the spatial resolution of this image is limited to an equivalent distance of the Earth's orbital diameter around the Sun, so that's 2 AU. Anything smaller than that simply cannot be resolved. Of course, the Jupiter-class planet here is probably more than 1,000 times smaller than this, which is why it appears as a smudge of light and not a clear disk. This means that even if the resolution were somehow improved by a factor of 1,000, say, you'd still only have a 1 by 1 pixel image of the planet. Now, if you wanted to image Earth-sized planets, then you'd need another factor of 10 improvement upon that, so now 10,000 times greater resolution. To make matters worse, the ALMA Observatory can only detect this exoplanet because it's only recently formed, meaning it's still incredibly hot and luminous. When it comes to imaging a cool, pale blue dot like our home, not only is it incredibly small, but it's also staggeringly faint. To combat these two problems, so that's resolution and faintness, the typical solution to both is just to build a very big telescope. But how big? In 2010, Jean Schneider and colleagues asked what the extreme limits of our technology might be for imaging other worlds, and this provides us some guidance here. For resolution, the basic limit is the so-called diffraction limit, which equals 1.2 multiplied by the wavelength of light being used, lambda, divided by the diameter of your telescope being used, d. Now, in microscopy, you can sometimes actually beat this diffraction limit by manipulating the source in various ways, but of course in astronomy we can't manipulate distant planets, and so this represents a fundamental limit. So, for a visible light photo, Schneider finds that you'd need a telescope that's about 70 kilometers in diameter to take a 10 by 10 pixel photograph of a super Earth-sized planet that's just 16 light years away. Now, in principle though, you don't actually have to build a single telescope that is 70 kilometers across though. Light from different telescopes, which is spread out over a 70 kilometer region, could be combined to achieve the same effect, a technique known as interferometry. This indeed is exactly how PDS-70 was imaged with ALMA, which has a baseline of 16 kilometers. The Event Horizon Telescope took this idea to the extreme, using telescopes across the Earth to famously image the black hole in Messier 87. To date, these astronomical interferometric images, also known as aperture synthesis, have been limited to wavelengths of light much longer than visible light. For example, this photo is really a microwave image. Visible light interferometry is possible, but it is an engineering challenge for the moment, requiring an ultra-precise calibration at the level of nanometers essentially. And yet, even using the entire Earth as a visible light interferometer would still not be sufficient to resolve exoplanets at the level of detail that we might truly aspire to. Look, a pixelated exoplanet image would be a groundbreaking achievement, but the ultimate goal would be to image the inhabitants of the planet itself, demanding far higher resolution. Imagine a video of a distant exoplanet light years away that is so detailed that we could see alien flora and fauna on the surface, that we could watch herds of wildlife migrate across the plains, we could watch the sentient inhabitants go about their day. The insights possible from such a video are truly unimaginable. Schneider and colleagues calculate that to pull this off, you need a telescope with an effective diameter of 600,000 kilometers, which is approximately the radius of the Sun itself. But resolution is only part of the story, remember. We also need photons. Distant exoplanets are faint enough as it is, but when it comes to the individual animals on the surface of those planets, they produce such a paltry number of photons that it's not enough to have two small telescopes spaced apart by 600,000 kilometers. No, you need a giant photon bucket, an enormous detector that is capable of not only spatially resolving those aliens, but actually detecting the light off them in the first place. Here the numbers get rather depressing. If the organism remains stationary, a 100 kilometer sized telescope could detect one photon per year from them at a distance of 5 parsecs away, which really isn't enough to even legitimately call it a detection. Now, if that organism moved at even a snail's pace of 1 centimeter per second, and we consider anything above a signal to noise ratio of 5 as being acceptable, Schneider calculates that you need a 3 million kilometer sized telescope, dwarfing even the Sun. What this calculation teaches us is that telescopes can only go so far, that remote imaging of distant exoplanets can only go so far. For even if we repurpose the Sun as a giant telescope, exploiting the gravitational lens effect in the outer solar system, even that would not be sufficient to resolve individual creatures on a distant exoplanet. Of course, there is a way that we can image inhabitants from space because we do it all the time to the denizens of our own home world. Because a fleet of Earth monitoring telescopes that point down rather than up orbit our planet right now. From foreign surveillance to climate observing, from national security to wildlife monitoring, clearly the capability exists to observe inhabitants from space. These telescopes don't feature any secret magical technology to accomplish this feat. The only difference is that by the standard of space, they're incredibly close. Take the Hubble Space Telescope as an example, still today our largest ever astronomy space telescope. This 2.4 meter diameter telescope cruises above the Earth at an altitude of 540 kilometers, which is about 75 billion times closer to the Earth's surface than the nearest star, Proxima Centauri. So if Hubble were to look at Proxima Centauri, the smallest spatial scale it could resolve in visible light would be about 10 million kilometers across, which is about 100 times larger than the radius of the star Proxima Centauri itself. But now turn Hubble around so it's looking down at the Earth rather than up into space, and because the Earth's surface is 75 billion times closer, that means the spatial resolution improves by 75 billion, and so that equates to a spatial resolution of about 6 inches or so. That's plenty enough to see people going about their day and resolve their activities. So this establishes that it is possible to resolve the inhabitants from space. It's just that you would have to fly all the way to that distant exoplanet, put a space probe physically in that star system to accomplish this. In fact, mission concepts like Breakthrough Starshot aim to do just that, with the goal of one day performing a high-velocity flyby of Proxima Centauri's planets. They would use a tiny gram-sized camera that would be shot through space like a high-speed bullet. Given that we're curious about what these other worlds look like at high resolution, and that we recognize the limits of remote telescopes, an interstellar probe is somewhat the inevitable endpoint of this journey of exoplanet discovery that we're on. And that makes you wonder, if we dream of one day doing something like this, perhaps an advanced alien civilization is already doing this to us. This idea was first suggested by Ronald Bracewell in 1960, with really the view of seeing this as an alternative path for us actually detecting aliens. Rather than listen for radio signals from distant stars, perhaps we should be looking around the solar system for probes that are monitoring us. These so-called Bracewell probes would presumably be close to the Earth and may have been operating for thousands or even millions of years, watching the Earth in case anyone intelligent ever evolved. After all, the Earth has been presenting a clear oxygen biosignature for some 2 billion years now. Such probes could even harvest energy from the sun, beaming back information to their home star about our development and behaviors. In a recent paper, James Benford highlights that this idea has often been overlooked by the community, and that he advocates for an active program to search for what he calls lurkers. As sci-fi as this idea might at first seem, let's try to avoid the knee-jerk reaction and just explore the science here openly. Now, in principle, many of the traditional tools that we've been using to look for alien transmissions could be easily repurposed to look for lurkers too. Rather than targeting our receivers at distant stars, we would simply target them at nearby asteroids, for example. And the Search for Extraterrestrial Intelligence program, SETI, is not limited to radio either. We could also monitor these objects for microwave or laser communication. However, in the case of the latter, the pencil beams produced by the transmitter would require us to fly our receivers into space in the hope of directly intercepting the beam. If we did ever succeed in eavesdropping on such a transmission, one can't help but wonder what it might say. The transmissions may also have some layer of encryption too, but even if they didn't, the very fact that they are not intended for us would likely render them undecipherable. The compression algorithm, data syntax and formats would all be completely alien to us, let alone the language or mathematical notation they're using. Even for highly communicative animals here on the Earth, such as dolphins using whistles and clicks, we still don't have the ability to translate human language into dolphin. Unless the aliens really did intend for us to decipher their messages by providing simplified data formats and specific keys for us to use, I think it's fair to say that the aliens need not be too concerned about the security and privacy of their communication system. Of course, here on the Earth, the privacy of our communications is far less secure due to the sheer volume of bad actors trying to find exploits for their own benefit. When accessing public websites or networks, it's become almost standard for our activity to be logged and tracked, with our anonymity lost as remote clients pin down our geographical location, behaviors, and whims. One way to fight back is to use a secure VPN online, which is why it's appropriate that our sponsor today is private internet access. It's really become a standard part of being smart online today to use a VPN, which diverts your internet traffic through a secure VPN tunnel, thus hiding your IP address and location. I use private internet access because it's an easy, low-cost solution. It's available on all platforms, from your computer to your smartphone. And with a single subscription, it covers 10 devices at once. Not only is your data encrypted, but private internet access have a strict no logs policy protecting you. You'll be able to unblock regional restrictions on streaming services, and you'll have access to their 24/7 support. You can try them out using the special link down below in the description, which will give you digital privacy for a little more than $2 per month, a 30-day money-back guarantee, and will even throw in 2 extra months for free. So it's a simple way to stay safe out there. Now, coming back to our alien transmission, if we can't decipher its meaning, all is not lost. The very fact that the signal is a laser or narrow beam transmission would immediately reveal it to be artificial, thus establishing that we are not alone. Yet more, at the source of that signal is a piece of alien technology in our own backyard, something that we could visit, salvage, and potentially reverse engineer. Some might question the wisdom and procedures here. Might it be dangerous to visit the probe? Could we trigger some kind of hostile, violent reaction? How would the USA respond to China visiting and even recovering the probe before they do? All of this is great fodder for science fiction, but in this video we're going to try and stay focused just on the science questions and leave the politics aside. One scientific question we can address is where this probe might plausibly be, which in turn can give us some guidance as to where we should be looking for them. Remember that if this probe intends to image the Earth at high resolution, then it really helps to be as close as possible. A low Earth orbit, or LEO, is ideal for observing the surface, but it is already intensively monitored using a variety of techniques such as electro-optical, passive radio, and active radar. The US Space Surveillance Catalog includes over 34,000 orbiting objects as of 2019, with sizes down to 10 centimeters. Of course, an alien satellite could be simply smaller than this and thus undetected so far. However, a 10 centimeter size, low Earth orbit telescope would be limited to a spatial resolution of 2 meters, which is really barely tolerable if you're trying to resolve the behavior of individual people on the surface. Perhaps this could be remedied with a network of interferometric, centimeter-sized probes, or even smaller, but a low Earth orbit is fundamentally problematic as such orbits are simply not long-term stable. In particular, atmospheric drag gradually deorbits such objects over a timescale of decades to centuries. Anything below 2,000 kilometers altitude will need periodic thruster adjustments to raise its orbit. Such a system is possible, don't get me wrong, but clearly there are also several reasons why a low Earth orbit Lurker is challenged by both our extensive monitoring of that region and the unnecessarily complicated mission profile that such a probe would have to have. Going further out, we might next look to the Moon. A probe that landed on the Moon would of course be perfectly stable from a gravitational perspective, as well as undisturbed by atmospheric erosion, weathering, or geological activity. However, much like low Earth orbit, almost every part of the Moon has now been extensively photographed and catalogued with orbiters over the last few decades. For example, the Lunar Reconnaissance Orbiter imaged the Moon's surface at a spatial resolution of 100 meters. So if there was a 100-meter sized alien telescope on the lunar surface, so it's hiding just beneath the resolution of our existing maps, it would itself have the ability to image the Earth's surface at a resolution of about 3 meters in visible light. So again, not enough to see the inhabitants. Here too then, we can say that our existing data already starts to put pressure on the idea of a useful alien telescope on the Moon. Obviously, beneath the lunar surface, anything is possible, but that would now sacrifice the ability to image the Earth in visible light. In his paper, James Benford speculates that the co-orbital asteroids and quasi-satellites around the Earth might be the best bet. Cruinia is a particularly interesting possibility. It's a 2-kilometer size co-orbital asteroid that follows a horseshoe orbit, taking it as close as 12 million kilometers to the Earth once every 770 years. Even if the entire 2 kilometers of this asteroid was some kind of giant alien telescope that was monitoring the Earth, it would still be limited to a spatial resolution no better than 4 meters of the Earth's surface. And that would happen at these rare, infrequent times of closest approach only. So again, I think this really isn't sufficient in isolation. However, Cruinia is just one of several known co-orbitals, with numerous smaller, sort of 100-meter sized objects now also known. So could these work together then to form an interferometric network? These co-orbital objects are thought to be stable on a timescale of thousands of years, but likely not millions, and they move around in wild, almost chaotic orbits with respect to one another, making interferometry a nightmare. Although I will just point out that the special Trojan orbits could be stable for far longer, although these lie at a daunting distance from the Earth of roughly 1 AU. So whilst it's possible that there are indeed alien lurkers hiding amongst these co-orbitals, I also think it's not an obvious and clear choice for an alien to use, with several prominent drawbacks. With Earth orbits and co-orbitals being unstable, perhaps the lurkers would choose a more distant vantage point where the Earth's gravity wouldn't destabilize their probe. But now we'd require a truly enormous space probe. For example, to optically image the Earth at 1 meter resolution from a vantage point around Saturn's distance would require a telescope roughly the size of our Moon. Alternatively, they might go the interferometric approach, but now the vast survey region we'd have to scour, and the sheer faintness of these probes would make them presently unobservable. Of course, with a few centuries of tech growth, that would likely change, but you have to ask, why would the aliens bother to build such an over-engineered system rather than just using our Moon for the sake of hiding themselves an extra few centuries when we're dealing with timescales of millions of years? This is exacerbated if one considers that civilizations spend much of their time indoors anyway, where their movements are of course hidden. So the most useful imaging would be of just primitive species where cloaking isn't even a concern. Put together, I think the case that there is a lurker imaging the Earth at high resolution and visible wavelengths is unlikely. Let me know if you see a way around this, but personally, given the stability issues and observational constraints that we already possess, the contrivance here is just a little bit too high for my appetite. I suspect that there are no aliens that are watching your movements either within the solar system or external to it. Perhaps a way to save the lurker concept is just to forget about imaging and assume that the lurkers are instead purely interested in monitoring our radio communications from the Earth. Now they need not worry about spatial resolution and could feasibly hide small receivers across the solar system. This again runs into some issues though. For one, just as we would be unlikely to ever be able to decipher an alien message that was not intended for us, they too would surely struggle to decipher any of our messages. This is not just about language, but the compression algorithm, the syntax, the data formats, and of course, and perhaps most importantly, the context that is necessary to understand what is actually being said. But maybe they just don't care about that. They just want to see how radioactive we are. But even here, I think the case is somewhat shaky. Because, after all, our radio leakage could be detected from far greater distances, feasibly even without ever leaving their home system, thus questioning the entire expenditure of flying all the way to another star system to do the same thing. But more importantly, radio is surely a transient technology for civilizations. Already humanity has started to transition away from radio, switching to methods like fiber optics, microwaves, and lasers, which are capable of far higher data communication rates. For example, the TESS L5 mission concept proposes to use a laser system to send data back to the Earth, which would essentially have no leakage, even for a lurker to eavesdrop on. The final twist on a lurker that we might consider is not really a lurker at all, but rather a probe that performs a flyby of the Earth. Coming back to the beginning of the video, this is after all the very concept that Breakthrough Starship proposed for Proxima Centauri. The motivation for a flyby here isn't to try and evade detection or anything, but rather simply because it's easier from an engineering perspective. Look, slowing down is hard, it takes propellant, it takes braking, and so it's simply easy if you just don't bother to do that and you just fly on by. Of course, the price of that is that continuous monitoring now becomes expensive, because now you'd require a fleet of space probes to be periodically visiting that planet and sending back their data. On the other hand, such a fleet would form a kind of daisy chain through space, allowing them to send back data across a system of relay nodes, and that would enable high data transmission rates. Michael Hipker has recently authored several papers about the idea of alien relay systems like this, and it certainly comes with major benefits as to how much data can be sent back home. Hipker even suggests that it could be sufficient for mind upload. Why travel between the stars physically when your consciousness could be simply transmitted? The possibility that we've already actually seen an alien flyby probe was floated recently in a highly controversial paper by Avi Loeb, who suggested that the interstellar asteroid Oumuamua could be exactly this. Check out our earlier video about this, which breaks down the forceful counter-arguments that have been levied at that suggestion. But even leaving those points aside for now, Oumuamua really doesn't fit the bill when it comes to high-resolution imaging of the Earth. With a closest approach to the Earth of 24 million kilometers and an estimated physical size of roughly 1 kilometer, an Oumuamua telescope could only have ever imaged the Earth at a spatial resolution of about 20 meters in visible light, clearly not enough to see the inhabitants. And yet more, the fact that it was tumbling around in space means that its optical system wouldn't even be stably pointing at us during its passage through the solar system. So to come to some final thoughts today, right now we really don't have any evidence for lurkers or alien space probes that are hiding within the solar system. And I think that anything that is large enough to optically image the Earth at 1 meter scale resolution should really be detectable with our current capabilities. Of course, we cannot truly exclude the hypothesis either, because perhaps the alien civilization has elected to hide their probes with some kind of advanced radar stealth or even an optical cloaking system. We have to be careful with such arguments though, because a perfect cloak is by definition unobservable, and so now you have a hypothesis which is untestable and unfalsifiable. That means it no longer crosses the bar of being a valid scientific hypothesis. In the end, even if the Earth is currently not being imaged at high resolution, it doesn't mean that we ourselves won't one day go on to build our own interstellar probes to do just that. Our journey of learning about nearby exoplanets is ultimately curtailed by the vast distances between the stars. One day, we will either have to accept this limit and just stay at home imagining what these other world surfaces might look like, or we'll decide to go. I can't imagine a point in this exoplanet journey where we say, that's enough. I don't need to know any more about this next door Earth-like planet. Our curiosity is so ravenous that it compels us to ask ever more questions about the universe. Ultimately, this scientific journey that we're on might have no end, and instead we might discover that it is the journey itself which defines who we are all along. So, until the next video, stay thoughtful and stay curious. Thank you so much for watching, everybody. I hope you enjoyed this video. Sometimes people ask me, how can we support Cool Worlds? Honestly, the best way is by becoming a donor to our research team, the Cool Worlds Lab here at Columbia University, just like our latest donor, Philip Masterson. Thank you so much for your support, Philip. So click the link up above if you want to join us. And until next time, have an awesomely cosmic day out there.